Alright, we'll go ahead and get started. So there were a few homeworks. If everybody remembers last Thursday, it was raining like crazy. So the graders kind of got the homeworks and got out of Gainesville before some of you had turned them in. So they've gotten them now. So if you don't have a homework grade on the website, it's probably, and you turned it in, it's probably just because you were in that small batch. Those should be returned hopefully soon. Another quick thing about the homework problems, I'm hoping that 1 will be a rare score. You're going to get a 1 if you tried to work out every part of the problem, but you made some sort of critical error. And I might have to remind the graders what a critical error is versus a trivial error. Because a trivial error, you should still get a 2. But again, that's obviously a judgment call. This is their first pass through the homeworks. I might push them in a direction so that in the future we have more 2s and less 1s. Another sort of thing just to point out is we are about one class period ahead of where this course has been in the past. So does anyone feel like I'm going too fast?
Yes.
No.
So we did leave a few minutes early last period because I kind of had that in the back of my mind. And if we stay at this pace, essentially what that means is that before the exam, we'll have a day where it's pure review. And we're definitely going to have that before the second exam because I'll be at AICHE in San Francisco. Your exam's going to be on a Thursday. I'm going to be gone both Tuesday and Thursday. Yeah.
Do you know what day it is?
It's on the syllabus. I don't have the dates memorized. Those are tentative dates, but hopefully that'll be what it is. I think one of is October 11th, and then the other one would be maybe November 16th, something around there. But like I said, the second exam will be during AICHE. You're definitely going to have a review period then because I'll be gone to class before. And if we stay a class ahead, then we will have a review period before the first exam as well. How many people are going to the Wednesday office hours? Okay. They're too far away. So I'm going to ask you guys, and so by a show of hands, I see this as 2 different options because I don't think it's working the way that it is. We're either going to move all of the TA's office hours back near Kim E, but we're not going to have a big room. We might not even have a small room. It's going to be like standard office hours where you guys are crowded into his office. I think we should do that, but we can either do it permanently or we can reserve the big room for the office hours before tests. So who wants to reserve the big room so that the Wednesday office hours before the Thursday exams, you guys can all attend and it's not crowded?
Are they in Norman Hall?
They're in Norman Hall, yeah.
I don't see anyone ever going there.
Even the day before a test.
No.
Where's that?
It can't be that far. So like a bus and a train, you gotta take I mean, we can talk about evening office hours for the day before test, if you guys like that idea. All right, is that a better idea that we try to aim for an evening, a late office hours before test? Yeah.
What, on Thursdays or Wednesdays?
The conference room or the room downstairs in the student center?
I don't think we can reserve the student center for office hours.
There's a room downstairs.
Oh, you mean one of the closed off rooms?
Right. And
Yeah, but I mean,
there's also
small rooms are not an issue. Small rooms are not an issue, but there's 130 of you. The room that we have is only 60. So we're already at most half the class can go there, and that's all the way in Norman.
Norman isn't really truly on campus.
Okay.
Or go through a tunnel. It's not really.
All right, so I'll talk again to the people who book the rooms, and we'll try to get something closer, at least for the ones before test, because I have a feeling those might be highly attended. The ones that are just standard, I think it's probably okay to just, you guys meet him in his office, or he can get one of the small study rooms, like the conference room. Okay, any other sort of administrative things, questions? Yeah.
The next homework is due Thursday?
Yeah, sorry, it's due not today, next Thursday. The email said today.
You said Tuesday last class. So.
I know. I was being lenient, and I said, I'll give them Thursday so that they have the Wednesday office hours.
Thank you. Thank you.
Anything else? Okay. So where we left off, we were talking about these Levenspiel plots. And I've had a couple of questions about these. For now, the shape of this curve is essentially going to be given to you. The data, if you've already looked at the homework, will be in a table, or there'll just be a plot printed in the book. We will talk about how to go from a rate law to a Levenspiel plot, but we just haven't taught you that yet. So as you're doing the homework, just understand that that's going to be given to you, okay? The last thing that we had talked about was putting different reactors in series. So what would this look like if I'm going to have a break in between two reactors at a conversion of 50% and I was using two CSTRs?
It's
Two rectangles, right. Okay, so this is two CSTRs. Is this more or less efficient in terms of volume than a single CSTR? More, right? Yeah, it's less overall volume than a single CSTR because we haven't filled in any of this region here. What about two PFRs? What would this look like? Same as one PFR. In other words, it's just the area underneath this curve plus the area underneath this curve, right? Are those my only two options? No, right? Yeah, I can mix, right? So two PFRs, the same area. What about a CSTR and a PFR? Which arrangement, given this intermediate conversion and this Levenspiel plot, would give me less volume? Going from PFR to CSTR, or yes. And you can kind of tell that by looking at these void volumes, right? How much will I save by converting the first CSTR to a PFR? Not a lot. How much will I save by converting the second CSTR to a PFR? Quite a bit. Is that always true? No. Again, it depends upon the shape of the plot. But even if I have this plot as it is, it'll also depend upon what that intermediate conversion is. If I have two CSTRs in series, what do you guys think? Is there a way that I can determine exactly what the intermediate conversion should be to yield the least overall volume? Yeah, I mean, of course there's a way, right? We're engineers. Graphically, though, that's supposed to be a straight line. It actually occurs at the point where that line connecting the two rectangles, okay, is parallel to the tangent of the Levenspiel plot. So it's just a graphical quirk. There's not a lot to say about this. You're not going to be asked on a test to derive the optimal intermediate conversion. It might be a good homework problem though. But yeah, I mean, what would the strategy there would be, right, is if you take the volume 1, that is FAO right? That's the formula for a CSTR. Everybody remember that? So the first volume of the CSTR is going to be equal to some intermediate conversion. That's what we're trying to find. And what do we have? We have the rate. That's the Levenspiel plot. And then the inlet flow rate. And then volume 2 is what? Is it FAO or FA1? FAO, that's correct. That's because we define conversion based on the inlet to the whole system. So it's a definition So what would my strategy be to find that intermediate conversion? Numerically, not graphically. Sure, that's obviously a good first step, is we add the two together and we get VT. Whoops. That's correct. And then what do we do?
You find the derivative equals 0.
Which derivative?
Take the derivative with respect to x1. That's what we manipulate.
Yeah, if I take the derivative with respect to x1, and I set that equal to 0, and then I'm going to rearrange and solve for x1. All right? Yeah?
Didn't last class when we defined volume 2, we had x2 minus x1?
Yeah, sorry about that. Yeah, it's the difference between the two conversions. Good catch.
And this is for trying to find the minimum volume?
Yeah, or, I mean, hell, you could use it to find the maximum volume too, right?
Okay.
But, yes. If you set the derivative to 0, you're going to find any maxima or minima of that relationship. And then, if there are two solutions, you guys should know how to figure out which one is bigger than the other. Okay, so the next thing that we're going to talk about, so just to catch us up and to look backwards a little bit, in the book, I'm not going to put all this on the board, but in the book, chapter 1 is mole balances and definitions. So we talked about some definitions very early on in the class. The mole balances are what we did last period. Those are the design equations, right? Where we wrote out the number of moles in is equal to the number of moles out. Chapter 2 is conversion and reactor sizing. Done. Okay? There's going to be more conversion and reactor sizing later, but he introduces the simple stuff up front, and then as things get more complicated, it's going to show back up in chapter 5. Chapter 3 is rate equations, and chapter 9 are reaction mechanisms. So that's kind of, we spent a lot of time on that already. And then chapter 4 is what we're going to talk about today, possibly next Tuesday, depending on how much we get through today, but that's stoichiometry. So we're, it's the entire chapter is just on stoichiometry and the effects. And then finally, chapter 5 is isothermal reactor design. So it's the same idea of this, really. It's sizing reactors, but now we're not going to make it so easy for you. We're not going to give you things like a Levenspiel plot, and it's not going to be something like A goes to B. It's actually going to be real systems where you've got to worry about flow rates, inerts, and all that stuff. But before we start talking about more complex systems, we've got to deal with the stoichiometry issue. So that's today. So we need a relationship between some concentration and conversion. Why do we need that? Why is that important for us? Why is that useful? Why don't I just keep things in terms of number of total moles or the flow rate of different species?
Because the volume is written in those terms, and so when you integrate, you have to put it all in the same terms.
That's certainly part of it. The volume's in those terms. What about the rate laws? What do we write rate equations in terms of, right? Concentrations. So that's why we want everything to be in terms of concentrations. It makes our lives easier. So the mole balances are expressed in terms of conversion, which is great. But it's in whatever their most convenient form, which usually means and the conversions are written with some basis in mind, right? We talked about that a little bit yesterday, or Tuesday. Usually A, if you're just in that generic A plus B. Fogler will just say, okay, we're going to define conversion in terms of A. So we need something that connects a rate in a function that we'll call G. So again, we want to write the rate as a function of conversion. That's the goal. What we have is the rate in terms of concentrations, right? And so again, we need something that converts from conversion to concentration. We need some function that relates these two so that we can combine these and ultimately get rates as a function of conversion. So let's take our favorite and recall, we've already done this, but we'll put it up anyways. Right? Everybody remember that? I can relate the rates of consumption or production of different species by their stoichiometric coefficients. Why are the stoichiometric coefficients on A and B negative? Because they're reactants, they're being consumed. That's right. So I can rewrite my equation up there right? Yeah, sorry. Okay, so for a batch reactor, we start with any of these species, right? I mean, presumably speaking, I could have reactants or products loaded into my batch. So we call that NaO.